But on the whole, you seem to have the idea. I think my grading was probably lenient as far as that goes. Where I took off, I didn't take off much. So just be sure to look at it and that you be sure you understand things, regardless of whether you got nearly full credit or something. Just a few things. Let's see. Problem one was about that was a density of states problem, and I don't want to go through it. I just want to make the important point. Well, we talk a lot about degeneracy, and one of the ways we describe degeneracy often is with the density of states. You know, thus far, when we've talked about quantum mechanics, we've used sums over discrete energy levels. And in fact, you know, for example, spectroscopically, there's actually always, or almost always, a slight uncertainty to the energy. It can't be described as completely discrete. And so we talk about the density of states often. So one of the problems was about that. And I just want to make sure we're thinking in the right manner. So for a particular problem, a degeneracy is defined. And it's defined as really the number of states between energy E and energy E plus delta E. So it's that delta E width. And you know, it's whatever the problem is, you could calculate the degeneracy simply as the difference between some function evaluated at E plus delta E and the same function evaluated at E. That's the definition of this. Let's call it a quasi-degeneracy, because it's many different energies, but all very, very close to each other. It's very typical to rewrite this as some function, and generally the symbol used is rho, that's the Greek rho, which is some function of the energy times that small width delta E. Very common to think in these terms. So the degeneracy itself is then this rho times delta E, the small spread in states. Obviously, as delta E gets small, so that's usually the way you see it written in terms of a differential, and this is called the density of states. So the problem asked you to figure out a functional form for the density of states, the rho. I noticed some of the answers ended up with something times a delta E, and all the math was perhaps correct, but strictly speaking, the density of states is just that part. Okay. So just I think that's all I wanted to say about that problem. The method was really, as in the book, the math was a little funky because it used a gamma function, but I didn't look real closely at the precise solutions. They looked like they were going the right direction. Yeah.
Which problem is this?
The very first one, so it's problem 1-25. Okay. The second problem, so that's all I wanted to say about that. Any questions? Okay. The second problem was, straight from thermo. It was changing partial derivatives sort of thing, and nobody had any problem with it, so no need to say anything. The third problem, so that second one was 1-29. I'm not going to say anything about it. Third problem was 1-46, and there, some people didn't quite seem to be setting things up properly. It looked like you maybe understood, but I couldn't tell. Let me see here what it is. So I wanted to say a word. Okay, it's about probability distributions and calculation properties, right? And that was discussed in a continuum sort of way, non-discrete way in the first chapter, chapter 1. I didn't deal with it. I just let you read it. And hence, after that, we've been dealing in terms of sums, not in terms of integrals. We've been dealing with discrete probability distributions, not continuous ones. But I want to make sure we can handle the continuous ones. That's classical statistical dynamics, thermodynamics, and we have a chapter on it later. So I just want to say one word about it. So the issue is then, suppose you have two F in this case is thought of as a probability distribution. For two different things, X and Y. In this case, they said, let's assume that X and Y are independent. So if X and Y are independent, then the probability distribution, it's a joint probability distribution, can be factored out. Now suppose that one has some property, and the property depends on X and Y, if you like, and we're interested in the average value of that property, then we can calculate that average value from the probability distributions in this way. Instead of sums, they're integrals. So it's a double integral over X and Y. Just as we've been doing, except we've been using sums instead of integrals when we're summing over our states, right? Now the convention is to choose a probability distribution so that when you integrate over all space, it's 1. So let's just assume we're talking about some normalized probability distribution. Then you get what's on top. Now, if X and Y are independent, then we can rewrite this as so the problem then asks you to show that for this property, we'll call it W, it's just the sum of X and Y, show that for that particular sum, the average of W is the average of X plus the average of Y. Show that. Right. That's what it's about. And they also asked you to show that the variance in W is equal to the variance in X plus the variance in Y. Right? So let me just take this one step farther and then I'll be done. Okay. I won't deal with the variance. So that's what the average value of W is, right, by definition. So I can simply factor things out. And this simplifies. And this, of course, since F2 is normalized, is just 1. Likewise, this is just, and that's that. So that's the idea. And for the variance, you go through the same kind of procedure. So what's the point here? The point is really this. This is the point. Everything else you can do. What's the definition of an average for something that's for a continuous variable? It's that. Okay. And what does it mean? This in today's into sort of chapter 5 especially, we deal with properties that are dependent or properties that are independent, and this issue of distinguishability and indistinguishability and the symmetry properties of the wave function. In those issues, dependency and independency are buried. So that's why this is an important concept right now. So I guess actually this and this are the two fundamental things to be considered. Questions there? Okay. So that was problem 3, and I think you can all handle that, but you didn't all set it up quite right. And one among you leaves off dx's and dy's all the time. Which is kind of understandable in a test situation, but not so understandable in a homework situation. So it's hard to know whether I know this is what the guy means, and therefore I'll say sure, but it's just hard to know if you really know what you seem to be indicating. And that makes it harder to guide and more time consuming. Problem 4 was a very simple problem about Lagrange multipliers. And that was 1-51. Nobody seemed to have any trouble. So unless there's a mad demand, I won't say anything more about it. Look it over, I guess. Number 5 was problem 1-56, and that was pretty basic, but not everybody quite got the idea, I think. So I'll say a word about it. At least one part of it. So the problem was, we were talking, and happened to be about heat capacities, but it could have been anything. That is the Einstein formula for the heat capacity of a crystal, I believe. And so you were asked to play with this in 2 limits. What's the high temperature limit? What's the low temperature limit? And there's another famous formula that Debye came up with that's a little more complicated, same kind of question. So I just wanted you thinking in terms of limits. That's all it was about. Could have been any formula, really. And so just one little point. The low temperature limit. Well, in the low temperature, there's not much you can do with this, but just notice that in the denominator, if t gets small, the exponent gets huge. So this whole term gets huge, and the 1 can be neglected. So then you do a little algebra, and you can see that you can cancel this out, and this goes to And that's about all you can do with it, right? So you just had to neglect this. So in certain limits, you can just neglect terms in a sum. The high temperature limit's a little different. In the high temperature limit, T is big, so this is small. The 1's definitely not neglectable. Can't do that. But you can expand. Another trick that just naturally comes to mind if you see an exponential is to expand the exponential. So this goes to the whole thing squared. Of course, 1 cancels out. And since we're talking about a high temperature limit when T is large, the first term is the only important term. The others are just, as the larger T gets, the less important they get relative to the first term. So we neglect everything except the first term in each case. Just neglect all of that. 1's the first term. Here we got rid of the 1 because of the minus 1. So this is the first term. Of course, it got squared, so this becomes, the whole business just becomes, which cancels that. So it's just, you all know this stuff, and it's reminding you to think in these ways. Okay, so that was it then for the problem, for the chapter 1 problems. Chapter 2, 2-5. Yeah, the famous, the entropy thing. Some of you seem to get it, some of you didn't seem to get it, so you either saw your way through it like this or you didn't. It's one of those things you see or you don't see it. So there's a really famous equation. That's why I like this, famous equation. I think I need a sum, don't I? Yeah. Yeah. Where P sub j is a discrete probability. So this is a discrete probability distribution. And the entropy is related to this log, with sum of logs. Now if you think about this for a moment, of course we think entropy is always positive, right? Or 0, it's never less than 0. Does it make sense qualitatively? Well, yeah, because Pj is always less than 1, so this log's always negative, times negative is positive. Okay. Really famous equation, and you may have, I know Joel made the connection, maybe others did too. In our speaker, Ralph Kaiser actually used an equation like this for entropy, some particular kind of entropy, in his presentation last Friday. So, anyway, so the whole point was to show that this is true. And the way in terms we've used, that's what P is for us, right? And this thing is just Q. So now you can begin to construct this sum So the log of this will simply be and that's basically the end of it. This you'll recognize as, what's that? In terms of an average.
Energy, right?
Yeah, exactly. This becomes minus beta times the average energy. Right? The average energy is just and then I think you can see your way from here to here, right? Just multiply by minus k and you'll, well. So this becomes minus k right? And that's our definition of S we came up with earlier. It's a kind of amazing little formula when you stare at it for a while. Entropy, I mean, I said last time or something that entropy is really just probability, right? Mm-hmm. So that was problem 6, or whatever. Whatever problem it was. Number 6 was, that was 6. Yeah, that was 6. The 7th one was again Lagrange. That was 2-6, which it was just the same thing as an earlier problem with one more thing thrown in, and we basically did it in class. So I don't think I need to say anything about that.
Professor?
Yeah.
For problem 6, I had it tucked in on a different page.
Oh, did you?
Yeah.
I was staring at it and staring at it. Oh, yeah. Well, let me just give you
Yeah.
more credit. Okay?
It's fine. Okay.
It's perfect.
I guess I did them together because they're so similar.
No, I did it.
I'll start.
I admit I watched the Murray match before I graded the homework.
I thought it was a good match.
So that is, let me just deal with this now so I don't have to deal with it later.
Oh, I didn't have it. Oh, that's my fault.
I kind of thought that was going to happen.
Thank you.
Yeah. All right. So problem 6, unless somebody has a question, I think we'll just leave it alone. Or problem 7, I guess it is, which is 2-6 is problem 7. Problem 14, I think you did fine, those who did it, but it's worth making a point. It's worth bringing up. Let's see where I get it here. Yeah, so we are going to see shortly, I think it's in the very next chapter, 6 or something, where we deal with the monatomic gas, that we will derive the partition function, the canonical partition function, and it turns out to be this. Right now, this is just being pulled out of thin air, but we'll get there. And I want to make a point with it. So you can see a couple things. The n factorial in the denominator looks just like, well, it's something we've seen before. It looks like there's some probability, and maybe there are in ways of distributing some set of energies perhaps. So you get 1 over n factorial. I guess n factorial is the number of ways, volume to the n. So it looks kind of familiar. Now we've seen formulas, ways to connect the partition function to thermodynamic quantities. Very familiar by now. The energy is 1. And pressure is another. So part of this is plug and chug. For this particular partition function, calculate these particular things. And this one turned out to be, the energy turned out to be 3/2 in kT, which looks familiar. That's the energy of a perfect gas, certainly. Nk, of course, if n is equal to Avogadro's number, Nk becomes the gas constant, R. And when you did this for the pressure, you found that the average pressure is nkt over V, and that's just the perfect gas, or the ideal gas equation. So at first blush, you say, wow, my God, it's amazing. Ideal gas equation falls right out of this. I trust them, though I haven't seen where it came from yet. Oh, how cool, you know. That's the first part. That's really why I assigned this problem. Okay, and then they made the point that it is cool, but it's not as cool as maybe you thought at first blush, because actually any time that you can separate Q into a function of temperature multiplied by the volume to the power of n, you're going to come to the same conclusion. I'm not going to go through it, it's not hard. Okay. So anytime Q separates in this way, temperature separate from volume in this form, then you'll end up with the perfect gas equation. Yeah, you can. If you didn't get it quite fully, you can go back and look at what I did. It's not hard. Questions? That brings us to the game. The game rhymes with game. And the game, the reason I put the game on there is partly because that's the way we think in stat thermal. We just think about probabilities. And it's a little tricky. It's all about joint probabilities, you know. Because not all the probabilities are independent in the way you think about this. So let me remind you of the game. The game was, we have player A and player B. Player A writes down, or says out loud, whatever, 4 different integers. And those integers can be any integer under the sun. Can be positive, can be negative. The only stipulation I gave is that they all be different. I'm not sure you need that stipulation, but it just is easier to go ahead and put it in there. All be different. And it's the simplest of things. This person just says an integer, and then another one, and another one. But he has to write them down first. You know, he's got to make up his mind first. Then he reads them one by one to player B, who at any point can say, I think that's the biggest one. And the question is then, what strategy should B choose so as to maximize his probability of being correct, right? And you can kind of think as sort of ground zero, the ground zero strategy, the default strategy of just randomly deciding ahead of time, I'm going to choose the 4th one, or the 2nd one, or the 1st one. That's going to give you a 25% probability of being correct, right? Just randomly choosing one of them. So the question then is, can we beat 25%? And several people got it right. I want to show you how I think about it. Well, the strategy, what's the correct strategy? the best strategy. Actually, so Armando wrote a beautiful, and he typed it up. I was really impressed. Everything else was hard to read, and then he typed it up. So the best strategy?
Yeah, don't choose the first one, and then if whatever number that pops out is larger than the preceding, you choose that.
Yeah. Yeah. So if the second one is larger than the first one, choose the second one. If you don't choose the second one, but the third one is larger than the first and second, both of those, choose the third one, and otherwise you choose the last one. So we know that the default sort of random thing gives you 1/4 of the time you're right. So can we do better? So what I constructed was I wanted to, for this strategy, which I believe is the best strategy, I wanted to construct a table and figure out, if you choose this strategy, if you follow it, what is the chance you're going to be correct? So the strategy will lead you to choose the second number in certain circumstances, and the third number in other circumstances, and the last number in yet other circumstances. And you can figure out under each circumstance what's the probability that you choose it and you're going to be right, or that you choose it and you're going to be wrong. So PW is the probability of winning with that choice, and BL is the probability of losing with that choice. So, and